Alrighty, going to 11.6, 11.7. These are going to include everything from the surface area of a pyramid and cones, but also it'll have the volume of pyramid and cones. So you have a definition up there. Pyramid is a polyhedron, which the base is a polygon, and the lateral faces are triangles with common vertex. The lateral faces are going to be an important part of our formula coming up soon. The lateral faces are always triangles in the pyramid. You'll see that in an example coming up. Let's see. Here's what you're writing down, probably in your notes, following along. What is a regular pyramid? Is the base. Its base is a regular polygon, and height goes to the center of the base. So in this left example, over on the bottom right-hand corner there, it's going to be one of our better examples of what we're going to be finding. I don't know what that little writing utensil was, but that's going to be our base, or kind of our default pyramid that we typically go to. On the right, we have an oblique pyramid. You don't run into those as often, but it's good to know where those different components go. The slant height, that's going to be an important part. It's always represented by a L like this, a cursive L, and it's going to be this part right here. People will mess this up all the time, and they'll call this the height of the pyramid. That is not true. The height is in the middle, right here. The slant height is right over, making the slant on the pyramid. And the Egyptians, I didn't mention this before, but Egyptians found that pyramids were one of the more stable of shapes, and that's why a lot of their structures were pyramids. They were big mathematicians, and that's where we get a lot of our math from. The Egyptians, they were pretty intuitive in their math capabilities and designs and advances in math. So pretty neat. But going forward with what we're doing, bases are the kind of the same idea as what we've done before. It's going to be the bottom of the shape. It's going to be that polygon at the bottom, the shaded region, right? And both of these are the base. And so we'll find the area of the base in our different formulas, and we call the top, the pointy end of it, the vertex. So there you go. So let's use some of those components to help us find the slant height of the pyramid below. Well, we know the slant height is not the middle here. This is the height. This is h, lowercase h. This over here, right? If you're at the vertex up here and you slid down, that's the slant height, right? You slide down the pyramid. You can't just drop through the top straight to the bottom. It's a slant. That's the slant height, L. Well, what we can do is make a triangle right here, imaginary right triangle. Well, we know that this is 100, right, over here, and then this is, cut in half, which is, again, 100. Well, we have a SRAD 2 situation here, right, going back to those different special triangles, right, triangles. So we can just call this slant height, L, equals 100 rad 2. Because this was 100, this was 100, so this is 100 rad 2. And if you punch that in the calculator, it should be about 141.421 feet. If you're getting a final answer there. So that's a good thing to know how to do. Great. Let's move on to find surface area of a pyramid. Nice formula. You're going to use this quite a bit. Big B is the area of the base, okay? Not just, some side of the base. It's going to be the area of the base. P, capital P again, is the perimeter. L, right? That's the same thing here. It's going to be our lateral height. So you got to be careful between height and then slant height, or lateral height. Those two words go hand in hand, slant height and lateral height. So And then this part of the problem gets you the lateral area like you've seen before. All right, so let's try this out. Okay, got some nice looking problems coming forward, and then we'll get to some cones after we're done with this. So a couple things you got to do here. First, you got to realize the base. Whoa. The base is a triangle, okay? And it's not only a triangle, it's an equilateral triangle. All three sides are 15, okay? So one thing, if you it's a throwback from, remember you throwing back in these two problems to 11.3 with some different formulas that we used before. An equilateral triangle was actually s squared times root 3, divided by 4. That actually got you the area. So if you just did this, you'd be done. I'll show you the other way, but this is probably the fastest way of doing this. So I do 15 squared radical 3 divided by 4. Are you going to be memorizing this? No, but you could have this on a quiz, right? You'll have the formula and then be like, oh yeah, that'll be perfect for what I'm doing here. Okay, so if I did that, I'd get 97.43 ish, something that affects centimeters squared. Okay, that's not their answer to the whole problem. That's just our base. We're finding surface area. But the other way to find the area, right, is cutting this in half, saying this is a 90-degree angle there. Then we have 7. Come on. This is a bad time for that to move. This is 7.5, right? Cut that in half. Okay, so now you can do a Pythagorean theorem kind of problem. And this is going to get us the same answer. We're just finding two different ways to find the base, and then the rest of it we have for our formula. 7.5 squared plus b squared equals 15 squared. You do all that kind of math there, right? You subtract 7.5 squared from the other side. I got about, I think it was like 12. I don't know if I have it written down. I could do it right now. 15 squared minus 7.5 squared. I think it was 12. Nope, totally wrong. 168. Oh, I know what's going on. You get 168.75, and then you gotta take the square root of both sides, and then you get about 12 point whatever. But you're gonna want to use this as the thing you punch in your calculator, because then you're gonna do base times height divided by 2, because we have a triangle, right? We're finding the area of that triangle. So base 15 times height. We just found the height. That's this. Divided by 2. Once you do this, you'll actually get the same thing, 97.343, whatever. Okay, so back to our formula. Try a different. Man. Okay, hold on. We need different colors. Go back to our formula to find the surface area for any pyramid. Area of the base, we just found that, plus 1/2 times the slant height times the perimeter. All right, so let's do that. We have the base, which is about 97.43. Now have the whole thing on your calculator so you get the right answer in the worksheets and things like that. Times 1/2, plus 1/2 times the slant height. Looks like that's 9 times the perimeter. Well, 15 plus 15 plus 15, that's 45. Now you punch that in the calculator. You should get 299.93. Hopefully that's what you get in the calculator. Sometimes even I can punch in things incorrectly in the calculator, even though you write things correctly here. So you do have to be careful in that regard. This other problem is equally as involved, where you have to find the area of the base there. But they still give you the slant height, which is pretty nice. You don't have to go find that. It's right there for you. We just need to find the base, area of the base. And you ran into this problem yesterday a little bit, where you had to find the area of a hexagon. If you didn't quite remember that one, you have to find the apothem. You have to go back to 11.3 and find how to use the formula for a regular polygon, which is 1/2 times the apothem times the perimeter. So we have to find the apothem. Okay, so we have this situation again. We've done these problems so many times, I just memorized that this is 60, okay, and I need to find this side. So now I have to use some trigonometry. I'll use a different color. Let's see what's going on. So it should have, right, opposite, adjacent, because I know that this is 2.5 down here. I cut the 5 in half to get this side right here. So if you're using your, trigonometry knowledge, you should know that you'll end up with, I guess I'll write the whole thing out. It should be tan 60 equals x over 2.5. All right, but if you simplify, if you get that down a little bit, you get 2.5 tan 60. All right, so that's going to be the apothem. If I punch that into my regular polygon formula, that's 1/2 times the apothem times the perimeter. Well, the perimeter is 5, 5, 5, 5, 5, 5 times 6. So that, because there's 6 5s there, hexagon. So we have 30. 6 times 5 is 30. This is going to be the area of the base of this stuff right here, right? All this hexagon area. That's what we need for our formula. Now, I'm going to write, let's see what I want to do. Yeah, what I like to do sometimes is just in the calculator, just have everything put in at the same time. You don't have to, but it is nice if you're just trying to find the answer without having to punch an answer over and over and over again. So it's going to be 1, if you're writing a kind of like that final formula for the surface area, and I'll use black. I'm going to have 1/2. I'm going to rewrite this. This is the base. I put this almost all in parentheses and then the calculator, right? Or you could write 0.5 over here. So it's base plus, I can even go check right now. What is it? Base plus 1/2 slant height times perimeter. So 0.5 times slant height, we just said that was 10 times 10 times the perimeter. We just found the perimeter is 30. Woo! That does look like a lot, but that's our formula from before. This is our surface area. Great. Punch all that in the calculator. You get 214. Well, I got 214.95. Hopefully it's around there. Like I said, if I type something in the calculator, that could be off, but I would think this is the correct way to punch it in. All right, that is the surface area for some polygons. Now, let's get to some cones. Hopefully this is a little easier because circles don't really change their shape as much. Cone has a circular base and height that meets the base at center. Here's our formula, right? This is area of the circle. And then this right here, this is also known as the lateral area. So it's the like cone part of your ice cream, right? It's the cone. And then this is the circular part down here. That's adding those areas together. Great. L is still representing that slant height. So don't forget about that. This is the normal height, right? So don't confuse those two. Especially comes in on our first problem, right? Do not make this L over here. This is the height. This is the slant height. So we're going to need that slant height. How nice. We have a right triangle there. So we can use Pythagorean theorem to go find that out. 5 squared plus 9 squared equals c squared. Should get about 106. I am going a little fast. But when you punch that all down, it should be square root of 106. I kind of forgot the formula. Let's go back and check. So you have pi times radius squared. All right, so let's go do that. We have all the things that we need here. Pi times radius is 5 squared plus, then it said pi times radius. Pi times the radius. What is it doing? Hold, please. There we go. Pi times the radius. We just said that was 5. What is it doing? Okay. Times the radius times the slant height, and we just found that was square root of 106. I hit everything? I think so. Yeah. Great. All right. So let's punch that in the calculator. Hopefully you got 204 point. Oh, whoa. Try it again. 240. 0.26 centimeters squared. Or centimeters squared because it's still surface area, which is area, not volume. Great. That's it. This next one, oh, how nice. They give us the slant height. We don't have to use Pythagorean theorem for that. We just punch in the punch in the formula. Great. So here we go again. Oh, I'll use a different color. Boom. Pi times radius, 8 squared plus pi times radius, 8 times the slant height, 12. All right, and that's it. Punch in the calculator. 502.65 millimeters squared. There. Alrighty. And that is day one. We will tack, I believe, volume tomorrow or whatever the next day is for our 11.6, 11.7 unit here.